circumcenter. The only things that we did not talk about was in-center. And so if you didn't do 5-2 at all, that's fine, but that just means tonight you have to do 5-2, and it is due tomorrow. The assignment you're going to get today is not due until when? Wednesday. Okay, today's Monday, it's due Wednesday. All right? Say it again. It's just Monday, girl. Long day, long week going. Here we go. All right, so just to review quickly before we jump in, because it's going to make more sense if you really are focused on what we learned last class. If I have a triangle and I draw in the perpendicular bisectors, remember those are going to go through the midpoint and make a right angle. It could go through the vertex. It does not have to go through the vertex. Depends on the kind of triangle. If you draw in all the perpendicular bisectors, and I'm just sketching them, but you would need to use a ruler and a protractor to really make them perfect, because you would want 90-degree angles right through the midpoint. But if you did that, then they all intersect at this point, which we called a point of concurrency, and we called the specific one made by the perpendicular bisectors the circumcenter. Everybody remember that from Friday? And we learned the circumcenter theorem, which said the circumcenter is equidistant to the vertices. So if you draw all the distance from the circumcenter to the vertices, those are all the same distance. Okay, that was the first point of concurrency, and that was our circumcenter theorem, our first theorem. So the second one today is the in-center. The in-center is the point of concurrency of the angle bisectors. So if you draw in all the angle bisectors, excuse me. So I'm going to draw those in. Those are going to go through the vertex and bisect the angle. So if I draw in these angle bisectors, and then this angle bisector, and pretend that those really look like they're bisected, then where they intersect, that's right, even though they're not, that point of concurrency has a special name, and it is called the in-center. And it is made by angle bisectors. Yes, angle bisectors. Okay, so if you draw in the angle bisectors, where they intersect will be at a common point called the in-center, and then the in-center theorem says that that point is not going to be equidistant to the angles, because that's what you just went through to create them. It is going to be equidistant to the sides, but when you draw that distance, it has to be drawn perpendicularly. So notice these little right angles. We talked about this on Friday. You don't measure the distance of something diagonally. You measure it perpendicularly. So when I say that the in-center is equidistant to the sides, when I draw that distance, I have to make sure it's forming a right angle. So from here, perpendicular to each side, those distances would all be the same. Okay, so here's what I do to keep it straight in my mind. If I go through the sides to make the point of concurrency, it's equidistant to the other location, the angles. If I go through the angles to make the point of concurrency, it is equidistant to the other location, the sides. Does that make sense? Okay. In this section on Friday, we talked about where the circumcenter lands. If it was a right triangle, where was the circumcenter? On. If it was an acute triangle, where was it? Inside. And if it was obtuse? Outside. Very good. Okay, so we're going to look at this as well for the angle bisectors. So again, they drew in your notes, which I should have given you. Do you guys all have this? Unlike the circumcenter, the in-center is not going to be on or outside. It is always going to be inside. So again, this is a perfect, always, sometimes never question for your test. And again, I would remind you, I said this on Friday, this is where those are going to come from. So your circumcenter can be inside, outside, or on, your in-center is always inside the triangle. If you draw an acute triangle, obtuse, or right, when you draw in those angle bisectors, it's always going to intersect inside. And if it helps you, you can go and add those little arc marks to show that these are the angle bisectors, and that this point, oops, I don't know why it's not letting me change it. It's not, oh well. This point is the in-center. Okay? And what we just said is the in-center is equidistant to the sides. So if you were to draw all those in, that is the same distance. That's your in-center theorem. And once again, they're going to try to get you to understand why that theorem is true. So if you look at the next slide, what you're going to see is your triangle, and then instead of the circle, remember last class period, we drew a circle around the triangle, and that's a really terrible job. Pretend that's a good circle. And what did we call this circle? What kind of circle? Circumscribed. And we said that the reason this was equidistant to the vertices was because those were all radii of the same circle, right? Okay, so same idea here, except now the circle is inside the triangle, so we call it inscribed. Wherever the circle is, if it's inside, it's inscribed. If the circle's outside, it's circumscribed. Because it's inside, notice what happens when you draw those distances to the sides of the triangle. What are all three of those distances? Say it again. Okay, they're inside the circle, but they're specifically what about the circle? The radii again, right? They are all the radii, just like here, these were all the radii. And that is why your in-center is equidistant to the sides of the triangle, because the inscribed circle those would then be the radii of that. Does that make sense? Okay. So an inscribed circle always touches the polygon at the sides of the polygon. So your inscribed circle touches the sides of the polygon. Your circumscribed circle touches the vertices of the polygon. Does that make sense? Okay, because you're going to have to keep those straight on your vocab test. All right, so then we have a few problems left on the back from 5-2. Once again, they're going to give you a picture. My best advice on Friday was draw the picture, mark the picture with what's been given, and then the questions to answer become super easy after that. So it says MP and LP are angle bisectors of the triangle. First thing I would do is put those markings that show their angle bisectors. So MP is bisecting the angle of the triangle, which means it must be bisecting angle M. And then LP is also an angle bisector, so LP must be bisecting angle L. And so let's mark it. Which means where two angle bisectors meet, point P is called what? In-center. Okay, so there's our in-center. And the in-center theorem says the in-center is equidistant to where? The side. So keep that in mind, that the distance from P to any side of the triangle drawn perpendicularly should be the same. Okay, it says find the distance from P to side MN. So what do we know the distance from P to side ML is? 5, right? This distance right here, drawn perpendicularly, is marked to be 5. So what should the distance from P over to MN be? 5. And so again, it becomes really easy. The distance from P to MN is equal to 5. Not hard, right? But you have to understand the theorem and understand which point does what and what does it say about them, and that's the hard part. Okay, one last example should be the same picture. And this time it says find the measure of angle PMN. So I'm going to go back and mark what I had originally. This was an angle bisector, and angle L was also bisected. And so now the question is, what is PMN? So find that angle PMN. We're looking for this angle right here. So tell me some things you know that might be helpful here. Okay, so this has been bisected, so this angle is going to be the same as QMP, whatever that angle is. Okay, MQP is 90. What else do we know? NLP is 50, so what else does that mean? All right, so that's probably where we need to start. This angle right here is 50, and the one next to it is supposed to be congruent, so this angle is also 50. What does that make that whole big angle L? 100. How is that helpful? Okay, so we know this other angle N over here is 20, and this whole angle L is 100. So if we add 100 plus 20, and subtract that from the whole triangle, which is always 180, what does that leave us with for our other big angle M? 60. So this big angle has to be 60, and we want how much of it? Half. So that means the measure of PMN is 30 degrees, because half of 60 is 30. Does that make sense? All right. Any questions so far on 5-2? Yes. All right, then let's look at 5-3. And 5-3 is where we're going to pick up with those other 2 points of concurrency. So we've learned 2 so far. We're getting ready to learn 2 more. And I'm going to start a little acronym going over here that's going to help us in the end. So far we've learned circumcenter and incenter, right? And what kinds of lines did we draw in to create the circumcenter? Perpendicular bisectors. And what kinds of lines did we draw in to find the incenter? Angle bisectors. Okay, so I'm going to start a little acronym that I came up with that helped me. If it doesn't help you, don't use it. If it does help you when we're done, use it, okay? So the next 2 things we're going to talk about are medians and altitudes. We've talked about perpendicular bisectors, angle bisectors. I'm going to add up here, by the way, that these are always inside the triangle. So it doesn't matter whether it is right, acute, or obtuse. It's always inside the triangle. Okay, next 2 things we're going to talk about, medians and altitudes. What are those? So we'll start with the definition of a median. A median is a segment that goes from a vertex to the midpoint of the opposite side. Has to go from the vertex to the midpoint. I'm going to warn you that a perpendicular bisector could also go from the vertex to the midpoint. It could, but does it have to go through the vertex? No. Does it have to go through the midpoint? Yes, because it's a bisector. What does it have to form at the midpoint, though? 90-degree angle. And notice that a median does not have to form a 90-degree angle. So a median could be a perpendicular bisector at the same time, but they do not have to have the same characteristics other than they both go through the midpoint. The median has to go from the vertex. The perpendicular bisector does not. The perpendicular bisector has to form a right angle. The median does not. Okay? So that is an example of a median. And the next thing we're going to do is look at what happens when we draw in all 3 medians. So I'm going to come over to this side of the board, do the same thing I did over there. Start with a triangle. I'm going to draw in all the medians. We're going to go from the vertex to the midpoint of the opposite side. From the vertex to the midpoint of the opposite side. Vertex to midpoint. And if we do it correctly, they should all intersect at one common point. Again, to get this for real, you should use a ruler and be precise, but I'm just trying to quickly estimate. This point of concurrency is going to have a special name again, and it's called the centroid. The centroid is the point of concurrency of the medians. So it's called the centroid. Yeah, some famous mathematician somewhere, right? Yes. Centroid. Okay, the centroid, we'll talk about in a second where is it located, but it also has a theorem. The theorem is not equidistant to anything. So whereas the perpendicular bisector and angle bisector's points of concurrency were equidistant to either the vertices or the sides, the centroid is not equidistant to anything. Instead, the centroid is located 2/3 of the distance from the vertex to the midpoint of the opposite side. That's pretty wordy, so let's try it this way. The centroid is going to split the median into 1/3 and 2/3. Okay? The 1/3 part is going to be the distance from the centroid to the side, and the 2/3 part is going to be the distance from the vertex to the centroid. So I'm going to write that down here. You can add it in your notes if you want to. If I go from the vertex to the centroid, that's equal to 2/3 of the median. Vertex to centroid is 2/3 of the median. So if the median was 15 units long, what is 2/3 of 15? 10. So the distance from the vertex to the centroid would be 10. Okay? If you go from the centroid to the side of the triangle, it will equal 1/3 of the median. So again, if the median is 15 units long, what would 1/3 of that be? 5. Does that make sense? Okay, so it splits the median into 1/3 and 2/3. The 1/3 is the part from, I wrote 1/2, I don't know why. Sorry. The 1/3 is the part from the centroid to the side. The 2/3 is the part from the centroid to the vertex. And oftentimes the pictures are drawn so that it's kind of obvious, but if you forget, or if you don't want to just assume anything about your picture, then you should know. Vertex to centroid, 2/3, centroid to side, 1/3. Okay? And then you're going to have to work with those fractions and be able to use your ability to work with those numbers to find those distances. Okay, so the medians intersect at the centroid. If I'm drawing in, and I don't think they do it in the notes on this one, do they? No, I want you to add this. So let's draw in a acute triangle, a right triangle, and an obtuse triangle. So it's not in your notes anywhere on this page. So add it in somewhere. Draw in your 3 different types of triangles, and let's investigate where will the centroid land. So I'm going to go acute, vertex to midpoint, vertex to midpoint, vertex to midpoint. So notice it landed where? Inside, outside, or on? Inside. Okay? So always, if it's acute, it's going to land inside. Go to the right triangle, draw in vertex to midpoint, all 3 medians. And we're just estimating where we think the midpoint is, just to make this quick. Where did it land? Inside as well, right? Where do you think it's going to land for obtuse? Okay, draw in vertex to midpoint. Estimate about where you think the midpoints are. Does it land inside? Yes, so just like the in-center, the centroid is always inside, right? Always inside, just like the in-center was always inside. We good so far? Okay, so that is your centroid made by medians. Medians go vertex to midpoint. Where they intersect is called the centroid. Centroid splits a median into 2/3 and 1/3. So now we're going to practice some problems. So in triangle LMN, RL is 21. SQ is 4. RL is the whole median here, and that whole distance is 21. SQ is just this little part here. The question here says find LS. So the first thing I would ask you is, what is point S called in this picture according to the markings? So when you get to the test, notice nowhere did it say you have perpendicular bisectors or angle bisectors or medians, right? You just have a picture, and you have to look at the markings. So you notice based on the tick marks that R is a midpoint, Q is a midpoint, and P is a midpoint, right? And that these are all lines going from the vertex to the midpoint. So the hard part when you get to the test is you've got to know that that means those are all what lines? Those blue lines. Those are all medians. And where the medians intersect is called the centroid. And so S is the centroid. And using that centroid theorem, we know that the centroid splits each median into 1/3 and 2/3, right? Hard part is when you get to the test, you've got to get that straight and be able to tell just by looking at the markings. There's no right angle marks. We're not dealing with perpendicular bisectors. None of the angles have markings, so they're not angle bisectors. Is that making sense? Okay, so now we're looking for LS. How much of the median is LS? 2/3. There's two ways you can work this. For those of you who can work with your numbers really well, you don't need to write anything down probably. You can figure out what is 2/3 of that whole length. For others, you may need to write down LS equals 2/3 of the whole line RL. And then plug in what you know. What is RL? 21. So what is 2/3 of 21? 14. And the way I think about it is divide 21 into thirds. What's a third of 21? 7. And you have 2 of them, so you have 7 and 7, which is 14. Does that make sense? Because you're not going to have a calculator, so you're going to have to be able to work with 2/3 of 21. Okay. Easy. Go to the next one. Again, you could write an equation, but you don't really have to on these with these numbers, so easy. So now they ask you to find NQ. Is NQ the 1/3, the 2/3, or the whole? The whole. They give you SQ, which is 4. Is SQ 1/3, 2/3, or the whole? The 1/3. The 1/3 is the part from the centroid to the side. So if one of the thirds is 4, then how are we going to find the whole? Times it by 3 to get a whole. So what is 4 times 3? 12. You don't have to assume. The definition or part of the theorem said from the centroid to the side is always the 1/3 part. The distance from the centroid to the vertex is always the 2/3 part. Okay? Another way to think about it is you could say if 4 is one of the thirds, then 2 of the thirds would be 2 times 4, which is 8. And 8 plus 4 is 12. What do you notice is going to be true about the 2/3 part compared to the 1/3 part? Always. It's always going to be double. 2/3 is always twice as much as 1/3, right? So the relationship between those two parts should be that the bigger one is always twice the smaller one. Everybody see that? Okay. All right, and that is really as hard as those get. The next thing you should see in your notes is another problem like what we did on Friday in class. Remember when we graphed our picture and we had to find the circumcenter? And so we drew in the perpendicular bisectors and we found out where they intersected. Okay, so this is similar to that, except this one says, and I skipped this, I need to go back in the notes. So before we go to this problem, I need to go back and point something out I skipped. So look back at this slide. The centroid is the most special out of the 3 that we've learned so far. The centroid is directly in the center. Centroid, center. It is also called the center of gravity. It is the point where your region will balance. So if you think about an actual triangle, if I wanted to balance a triangle, let's see if I have a triangle in here. Maybe. Okay, pretend this is perfectly triangular. It's kind of curved because it folds to make a triangular pyramid. But pretend this is perfectly triangular. If I wanted to balance this on my pencil, then I would have to find the centroid to find the balancing point. If you think about this like a baby mobile, if you've seen mobiles that hang over baby cribs and they have things that hang down, if you don't want that mobile to tilt one way or the other, you want it to stay flat so that the objects are all hanging perfectly, then you need the string that you're going to attach to that baby mobile to be right at the centroid, the center of gravity. That way it will balance. Does that make sense? Okay, so it is the most special because it's the center, it is the center of gravity, it is the balancing point. So what makes this even a little bit harder when you get to the homework or the test is you have to look for those keywords. Notice it doesn't say find the centroid anywhere. It doesn't say that you have medians. It says a sculptor is shaping a triangular piece of iron that will balance on the point of a cone. At what coordinates will the triangular region balance? And so when you see that word balance, you're going to think, oh, the balancing point is the center of gravity, which is the centroid. And centroids are made by drawing in what lines? Medians. That's the thought process you're going to have to go through in your mind. So then that means to find the centroid, we're going to have to draw in all the medians. Do we really have to draw in all three medians? Only two, right? Just like Friday, as soon as two intersect, the third one's going to have to go right through that same point. So you really only need two. Where do medians go from and to? Vertex to the midpoint. So we have to figure out where is the midpoint of a side and then draw the line that goes from the vertex to that midpoint. Okay, so again, we're just using our midpoint formula. I'm going to label this A, B, and C just so we can talk about it. Which side do you guys want to find the midpoint of first? BC? Okay, so this side right here. So we're going to draw a line from A over to BC. We need to find the midpoint of this side. So let's do midpoint of BC. To find the midpoint, remember you average the x's and average the y's. So we're going to add which two numbers? Careful, I'm doing B and C. 10 plus 8 and divide it by 2. And then I'm going to add 7 plus 2 and divide it by 2. So we end up with 18 over 2 is 9, and 9 over 2 is 4.5. So that means we're going to plot the point 9, 4.5. That's our midpoint, and we're going to draw a line from the opposite vertex over to that point. You're going to really want to use a ruler when you're doing this to be precise, not really bad like I just did, okay? But for right now, we're just kind of estimating in our notes. But you'll want a ruler on your homework to make sure it's precise. Okay, so that's one median. We need to draw in another one. A to C. So we'll find the midpoint of this side, and then we'll go from B over there, correct? So let's do the midpoint of AC. All right, average your x's. What are we adding? 6 plus 8 divided by, and 6 plus 2 divided by 2. So that gives us 14 over 2 is, and 8 over 2. So we have a midpoint at 7, 4. Is that okay? Okay. And then we're going to connect B over to that point. And we're looking for where those two lines cross. And where do they cross? 8, 5. So it says at what coordinates? So the answer should be 8, 5. Use a ruler to be precise. We're going to look at one in a minute where it does not come out to be a nice, perfect, pretty whole number. And we're going to talk about what do we do if it's not perfectly in the corner. Okay? So use a ruler to make sure you're precise. Any questions? Hey, Jake, how are you? I'm good. Thank you, sir. Elena. Is it just you? Yep. This is for PSAT. This is your testing room information and the nice little study guide for you to just go through and look at. Awesome. All right. Any questions so far? Okay, moving on. October 16th for sophomores. Okay. So for the PSAT, it will be sophomores and juniors that have registered to take it. So sophomores are doing, all the sophomores are taking it, and only the juniors that chose to take it, that want to do it for National Merit Scholarship qualifying. The freshmen are doing the ACT Aspire interim on the same day, and then the juniors are doing something else, and seniors are having like a college and career day. Okay. All right, so now we're going to look at our last line, which is the altitude. And so when we do this project on Tuesday, the project is going to be over these 4 different kinds of lines and points of concurrency, and it's going to put it all together, and we're going to make a fun little color-coordinated study guide that you'll then get to keep and use to study with after you turn it in for a grade. We'll do part of it in class, and the rest of it will become homework, and that will be your assignment for the day. Will just be to complete the project. So it'll be a little better than book work and problems. Okay? All right, so we have another triangle. This time we're going to draw on what are called altitudes. When you think of the altitude of something, what do you think of? The height, and that is what altitude is. Altitude is a perpendicular segment that goes from a vertex, again, different than a perpendicular bisector, which does not have to go from the vertex. Altitude is perpendicular, but it goes from the vertex to the line that contains the opposite side. They could just say from the vertex to the opposite side, but we're going to look at what happens on obtuse triangles, and that won't work. So it's perpendicular from the vertex. So if I have a triangle here, my altitudes would go from my vertex perpendicular. Does it have to go to the midpoint? No, it is not a median. It is not a perpendicular bisector. They could all 3 be the same line, though. You could have a perpendicular bisector that is also the median, that is also the altitude, if your triangle is a special kind of triangle. But they do not have to be the same thing. So vertex perpendicular, and vertex perpendicular. These would be altitudes. And the altitudes, if you draw them all incorrectly, should intersect at a common point. And that common point is a point of concurrency. And for the altitudes, we call that the orthocenter. And it is our final point of concurrency. And I'll explain my little acronym over there in a minute. So the orthocenter is the point of concurrency for the altitudes. So in your notes here, orthocenter is the point of concurrency of the altitudes. Once again, in the notes, they don't investigate where does it land. So we're going to draw in an acute triangle, an obtuse triangle, and a right triangle, just like we did over here. So if you want to draw that in on your notes with me, make yourself an acute triangle, a right triangle, and an obtuse triangle. Caden, we miss you if you're watching this video. I'm drawing this on the whiteboard. I got it. But Edwin's got you, so he will show you what he has when you get back. We do miss you, Caden. Alexis misses you the most, but we all miss you. Love you. All right, so let's draw in all these altitudes, okay? So in these triangles, you're going to draw in your altitude. So again, altitude, vertex, perpendicular. Vertex, perpendicular to the opposite side. Vertex, perpendicular to the opposite side. And if we do that correctly in the acute triangle, where do you notice it lands? Inside. Could be the center, but it doesn't have to be the center. It is definitely inside, though. Depends on what kind of acute triangle you have. Okay, go to the right triangle. You're going from the vertex perpendicular to the opposite side, which is easy to do from the right angle's vertex. But what happens when you go to either of the acute angles vertices and you draw it perpendicular? It is the side of your triangle. The altitude turns out to be the side of your triangle, right? So in a right triangle, that's why we call the height of a right triangle one of the legs, because it is the altitude. It is the height. Mm-hmm. That's right. Tyler was right. Hypotenuse leg is height leg. All right. So if we go from the other acute angle over to this side, notice that it is also the side of the triangle that makes the right angle. So where do those three lines actually end up intersecting? On, and it is on the right angle, right? Right on the vertex of the right angle. So if you look at the perpendicular bisector from Friday, when it was acute, it was, oops, that's right. When it was acute, it was inside. And when it was a right triangle, it was on, but it turned out to be on the hypotenuse. Over here, it is on, but it's on the right angle. Okay? So obtuse is the other tricky one. It's really easy to draw from the obtuse angle. Just go across and make a right angle. But the harder part is trying to go from the other acute angles, right? And that's why in the notes, if you look back, when it identified the definition for altitude, it didn't say from the vertex to the opposite side. It said from the vertex to the line containing the opposite side. Because you cannot go from the vertex over to the opposite side and make a right angle. So instead, you're going to extend out that opposite side, and you're going to go down to that extension to make your right angle. Good. And then the same with this one. You cannot go from this vertex over to the opposite side without extending out that opposite side. So we're going to extend it out, and then we're going to draw a line that's perpendicular to it. Sorry. It's in your picture on your notes. If it helps, it's just a little hard to tell it on the picture in the notes. Now notice, do those three black lines I have up here on the board, do they actually intersect? No, not if they're segments, but what would happen if we extended them on out so that they did go on and go on and go on? It would intersect, and it intersects outside the triangle. So it's actually the same as what's over there. If the altitudes intersect to form the orthocenter, they have the same relationship of where they land as the circumcenter from Friday. If it's acute, it's inside. If it's obtuse, it's outside. And if it's a right triangle, it's on the right triangle. It's just where the location of on is different. Does that make sense? There isn't anything special about the orthocenter that we have learned so far. There's not an orthocenter theorem other than to say that the orthocenter does occur in an obtuse triangle. It looks like it doesn't occur, but it does occur. The orthocenter lands outside the triangle if you extend them on out. So everyone has had a theorem with something special. Either it was equidistant to the sides, equidistant to the vertices, or 2/3, 1/3. When you get to orthocenter, there's nothing special that we're going to learn in geometry. There is stuff special about it. If you go into higher level math, you're going to talk about a famous mathematician called Leonard Euler. And he has a special theorem that he came up with and describes the relationship between your circumcenters, incenters, centroid, and orthocenter. But we're not going to learn that in this class right now. Okay? If you want to know about it, you can Google it online. But you will talk about that in higher level math one day if you go too far. Okay? Too far. I say it's too far. I say too far. You may say not far enough, but all right. So here is my little trick before we go to this last example with the graph. So when I started trying to learn this so I could teach it. I was having a hard time keeping everything straight, and then I had to know where all this stuff was, and I had to be able to explain it, and I didn't need to be looking back at notes to try to remember what I was telling my students. So what helped me was to come up with a little acronym. And so I say, do you have a psycho pa or a psycho ma? Are your parents ever a little psycho? I can be a little psycho. Would you guys agree at a football game I might be just a little bit psycho? Just a little bit. Woo! No, probably not. Um, but I will say I get a little excited at a football game or a basketball game. So I can be a little psycho when Brendan doesn't pick his clothes up off the floor or something like that. So if you can remember Psycho Pama, this is kind of my little way. It's not spelled psycho like really you spell psycho, by the way. Psycho is Psycho. Okay? So psycho, that's how you spell it. I don't want you to start spelling psycho wrong. But this is one way to think about it, psychopoma, and that's how I kept it straight in my mind. So I'm going to show you what this stands for. You can copy it down if you want to. And I'm going to rewrite it this way. So psychopoma. C stood for our first one we learned, which was circumcenter. And the circumcenter is made by the first letter in PAMA, which stood for perpendicular bisectors. And I'm going to abbreviate there just to make this quicker. There are two A's in PAMA, so the way I keep them straight is you keep your bisectors together. So perpendicular bisector starts it, so the second A has to be angle bisectors. Keep your bisectors together. And the angle bisectors, when they intersect, form the point of concurrency called the incenter. It also helped me that this is the order in which we learned them, so sometimes that's helpful for you when you think about how did I learn it, the order might help. The next line that we talked about today was the median, so that's our M. And medians create what point of concurrency? Centroid. Now this one's a little hard because you have two C's and you've got to keep straight which C is which. So did any of your English teachers ever teach you I before E except after C? Okay, if they did, that's helpful. If they didn't, you're going to have to come up with something that helps you. But I always learned when you were spelling I before E except after C, except we're going to say I before E even after C. So this is I before E. So C-I, C-E, I before E. So if you can think about that I before E, except after C, I before E, even after C, we're going to put our C's I before E. Does that make sense? Okay, and if it doesn't help you, come up with something that does. And then our last letter is our altitudes. And we're keeping that straight from the other A because we're keeping our bisectors together. So we know the last A has to be altitudes. And the altitudes form the orthocenter. Now, this will help you whenever you get to the problem and you're like, oh, wait a minute, I'm on my vocab test and I've got to remember, what's the point of concurrency of the medians? Write down psychopoma, medians, you'll know the third letter goes with a C, I before E, it's centroid. It will help you on the vocab test. It'll help you when you get to the actual test and you're trying to remember if it says find the orthocenter, you can go, oh, psychopoma, orthocenter is matched up with A, keep the bisectors together, so it's the altitude. Okay? The other thing that it helps you with is all of this inside, outside, on information for those always, sometimes, never questions. Because notice the ones on the inside of the word psychopoma, the incenter and the centroid, were the two that were always inside. Yes. Because I had to do something, right? I don't know. Just played around with what I knew. Yes, it works out nicely, doesn't it? Okay? So, yes, so if you think about the ones inside the words, psycho, the two on the inside are always inside the triangle when it's talking about where they're located. The two on the outside have the same characteristic. So the two on the outside, I don't know why I circled this here. I don't really need it there. The two on the outside have the same characteristics. So these two are the same. If it is acute, then it's inside. If it's obtuse, it's outside. And if it's a right triangle, it's on. And those are the kinds of questions I'll ask you for always, sometimes, never. The circumcenter is always, or circumcenter is blank inside a right triangle. And you would say circumcenter is right triangle, never inside, because it's always on. Does that make sense? So you can think about that in terms of psychopomma. Okay, if it's helpful, use it. If it's not helpful, don't. It's just I had to come up with something to keep it all straight in my mind, and that's something that helped me. Okay? So 4 points of concurrency. We're also going to spend the entire day tomorrow creating this project that you can use then to use to study with, and we'll color code it with colored pencils. Last one we need to do here is graphing and finding the orthocenter. And this is going to be the hardest one we're going to do. So yes, grab some graph paper. You might already have some that you used Friday for your notes that you may want to keep. Since Caden's not here, I'm going to do this on the board. But I will warn you that this one is so close, you need a ruler. So make sure you grab a ruler too, sorry. And so it may not work as perfectly on here, Caden, if you're watching this, as it will if you use graph paper. Yeah, that's all right. Good. So when you click the link every time on Remind, when I send you the link to the video, it's just taking you to the YouTube video that's posted. Say it again. Yeah. So if you just go to YouTube and look for Angela Lashley, then you'll see where they are. The only thing on there is all the videos I use are on there. So there may be a 5.3, 5.4 video that was made for the kids that I have in regular, or it could be my other pre-AP. So, yeah, it's fine. I'm not trying to become famous on YouTube. The only reason I have the YouTube is to post videos so I can send you a link to it. So, okay. I am not posting videos of anything else other than math. All right. So let's. Yeah, that could be bad. Okay. So let's post our coordinates here. We've got 3, -2. And 3, 6. Need one more there. And 7, 1. And draw your triangle. Is that correct? Is that how yours looks? Okay. So label it XYZ, graph the triangle, and then again, when you get to the test, if it says find the orthocenter, first thing you're going to have to think is, what do I need to draw in that even makes an orthocenter? So you go to psychopomma, you think, O orthocenter matches up with A, altitudes, I need to draw in altitudes. Well, what are altitudes? Where do they go from and to? Vertex, perpendicular to the opposite side. So easy one, I agree with Edwin, would be going from Z over to our vertical line YX, right? So if it's vertical, what kind of line is going to be perpendicular to it? Horizontal. So easy one would probably be to draw that one in. So I'm going to go from Z straight across horizontal, perpendicular. There's my line. Okay. The next thing I need to do is draw in another altitude. And how many do we have to have total? 2. 3 we can, but 2 is all we need to find out where they cross. So do we want to go Y over to XZ or X over to YZ? Okay, I heard a couple different ones, but I'm going to go with y over 2xz. Is that okay? Okay, now here's the thing. You can't just estimate where you think it is. You have to make sure you're drawing it so that it is perpendicular. So what do we know about perpendicular lines? Okay, they will make a right angle, but in order to make that right angle, we need to use opposite reciprocal slopes. So we don't need midpoint, but we need slope. Okay, so we're going to find the slope, and I'm going to write the word slope so you don't get confused when you look back at your notes and think midpoint. We're going to find the slope of the line we're drawing it to first. So what line are we drawing it to? XZ. Okay, so what is the slope from X to Z? It's on a graph. You can just count there. So we're going to go up 3, is it? And then right 4. So our slope is 3 over 4 because we went up and right. So we want to go from y with the opposite reciprocal slope. So what is the perpendicular slope? Negative 4 over 3, right? So we're going to go from y, down 4, right 3. So from y, go down 4, right 3. And you could do it again if you want to. Down 4, right 3. It's going to be somewhere about there. Oops, I lost it. Use your ruler. Do they cross at a perfect ordered pair whole number where the two green lines intersect? And again, mine's not going to be precise because I estimated the graph up there on the board. Use your ruler and be perfectly precise. Do they cross at a perfect whole number? No, they do not. So that means that we're going to have to find those coordinates a little bit different than what we've done on the other ones because the other ones were nice, pretty whole numbers. But I want to preface this with, we could do what we're getting ready to do on any of them. The circumcenter from Friday, the centroid from today, or the orthocenter. We could do this next process on any of them if they don't turn out to be nice, perfect whole numbers. Okay, so what we're going to do is we're trying to find out where these two green lines cross. Think back to Algebra 1. When you were looking to find out where two lines intersected, instead of doing it graphically, you wrote their equations and you used substitution or elimination method to find out their solution. That's what we're going to do. We're going to write the equations for these two green lines, and then we're going to solve those two equations by substitution or elimination. So let's start with the first one we drew, this number 1 here. It is a horizontal line, and what is every horizontal line going to have for its equation? You were right the first time. Y equals what in this case? 1. Okay, it's an easy equation to write. Agreed? Okay, then we're going to write the equation for the second green line. And the easiest way to write that equation is probably going to be in point slope form because we don't have the y-intercept in the picture. But we know a specific point that it goes through. That was y, the vertex. So we know for sure it's going through this point. And we know what its slope needs to be because that's the opposite reciprocal slope. Does that make sense? So if we put it in point slope form, y minus y1 equals m times x minus x1, then all we have to do is plug in our slope and plug in our point from the vertex we know confidently it's going from. So what's going to go in for y1? Y minus 6 equals, our slope was what? Negative 4 over 3. Make sure you're using the opposite reciprocal slope. And then it's going to be x minus 3. So we plugged in the vertex that we were drawing it from, and we plugged in the opposite reciprocal slope. So now we have these two equations, and we want to solve them so that we can figure out what is x and what is y. So do you want to do substitution or elimination? I would do substitution as well. What are we going to substitute, Edwin?
1.
We can substitute the 1 in for y, right? And that will probably be the easiest way to work it. So let's come over here and do that. Substitution. So I'm going to have 1 goes in for y. 1 minus 6 equals negative 4/3, parentheses, x minus 3. Let's start simplifying. What's 1 minus 6? Negative 5 equals negative, do we want to distribute? Okay, so we're going to distribute this. So this will be negative 4/3 x. What is a negative 4/3 times negative 3? Okay, so it'll be positive 4 because it'll be 12 over 3, which reduces to 4. Or remember, the 3's can just cancel and you're left with positive 4. Does that make sense? Okay. What do you want to do from there? Subtract the 4 from both sides. So now we have negative 9 equals negative 4/3 x. What do we do from there? Okay. Multiply both sides by not negative 4 over 3 because that's the same thing, so it won't make it go away. We want to multiply by the reciprocal. We want to divide by negative 4/3, which is the same as multiplying by the reciprocal. So we want to multiply both sides by negative 3/4, the reciprocal. Which cancels out the negative and the 3 and the 4, so we're just left with x. And then what is negative 3/4 times negative 9? Positive 27 over 4. Let's write that as a mixed number. How many times will 4 go into 27? 6. 6 times 4 is 24. So how many do we have left over? 3 out of 4. So it looks like on your paper, if you're not super careful, it looks like they do cross at Z71. But they don't cross at Z71. If you did it really precisely, you'll see that they actually cross at 6 3/4 is our x value. And what was our y value? 1. Remember, we started with y is 1. So 6 3/4, comma, 1 is your actual answer for the orthocenter. So here's the deal. All 3 out of the 4 you're going to have to be able to do on graph paper. Angle bisectors we won't do on graph paper. But perpendicular bisectors, medians, or altitudes, I may ask you to find the circumcenter, the centroid, or the orthocenter. If they cross perfect and pretty, then you just write down those coordinates where they cross. If they don't, you write an equation for each of your 2 lines, and then you solve that system of equations by substitution or elimination. Okay? And then whatever you get is the point where they cross, which will be the answer to the question. Any questions? Was that the last one in 5-3? All right, let's look at 5-4. Okay, so 5-4 is just one theorem. That's all there is to it, one theorem. And I'm going to show you the easy stuff first, and then we're going to come back and actually apply and prove the theorem. So first thing I want to show you is what is the theorem and what the theorem is about. The theorem is about a triangle's midsegment. So it's called the triangle midsegment theorem for this section, but first we have to understand what is a midsegment of a triangle. So I want to make sure you're not getting too much information. We've got 4 kinds of lines right now. Perpendicular bisectors, angle bisectors, medians, and altitudes. Those are lines or line segments, depending on if you keep going or not. Here is a 5th kind of line, the midsegment of a triangle. It does not form a point of concurrency. These are the only 4 points of concurrencies, okay? A midsegment of a triangle is simply a segment that joins the midpoints of 2 sides. So mid-segment is going to join the midpoint to the midpoint of 2 sides. But if you think about a triangle, how many sides are there? 3. So when I think about that, that means I've got a midpoint here, a midpoint here, and a midpoint here, right? So I could have 3 different midsegments, just like I can have 3 different perpendicular bisectors and 3 different medians, right? This would be a median, XY, or this would be a median, XZ, or YZ would be a median. So you have three different medians. Three different mid-segments. Mid-segments connect midpoints of two sides of your triangle. Okay, so three different mid-segments connecting midpoints. Did I say that correctly to where it's clear? Midpoint to midpoint, mid-segment, okay? When you look at this, this creates a little triangle inside the triangle. That little triangle is called the mid-segment triangle. It's made by the mid-segments. Okay, just let's talk about what you think might be true here, just to come up with some things that might help you on the homework. Think about the perimeter of the great big triangle. This mid-segment is going to be how much of this side over here? Half of it. This mid-segment is going to be how much of this side over here? Half of it. This mid-segment XZ is going to be what compared to QR? Half of it. So what do you think the perimeter of a mid-segment triangle is compared to the perimeter of the big triangle? Half. Okay. So your mid-segment triangle should have half the perimeter. Good. Now let's think about area. When you look at those triangles that are inside the big triangle, how many of them are there? 4. And the mid-segment is just one of those 4. So what do you think the area of the mid-segment triangle is going to be compared to the area of the big triangle? 1/4. So it's going to have 1/4 of the area. Okay, that might help you on the homework if you have questions about that. Okay, so what is the mid-segment theorem? Before we do this, this example is where you have to basically prove it without writing a proof. It's going to show it algebraically why the mid-segment theorem is true. We'll come back to it, but first let's look at what the mid-segment theorem says. Because that's the longest, hardest one. So the mid-segment theorem simply says the mid-segment of a triangle will have two characteristics. One, it's going to be parallel to the opposite side. So every mid-segment will be parallel to the side across from it. And it's going to be, which you guys already said, it's going to be half the length of that side. So it's got two characteristics. It's parallel to the third side, and it's half the length of that third side. So if you look at DE here, DE is going to be parallel to AC, and DE is going to be half of AC. And every mid-segment will be parallel to the opposite side and half of the opposite side. Okay, and then I'm going to warn you about tricky questions on the homework. When we talk about parallel lines, we can't forget what we learned back in chapter 3. When two parallel lines are cut by a transversal, then we have those corresponding angles that will be congruent. Keep that in mind when you get to the pictures. That's going to be super important. This would be another transversal, so we have some more corresponding angles here. Do you guys see that? So watch for that, because you may use corresponding angles or alternate interior angles or same side interior angles, but you're going to have parallel lines all over the place with those mid-segments. So watch for angle measures that you can use with those parallel lines. Okay, so then simple questions. You should have 2 examples left and then the one we skipped. And these are easy problems. It says find each measure, BD. So we need to find the distance from B to D. What do we know about point B in the picture? Okay, point B is a midpoint. BD is a mid-segment. D is also a midpoint, right? And midpoint to midpoint is a mid-segment. Vertex to midpoint is a median. But midpoint to midpoint is a mid-segment. And so now we know that that mid-segment is how much of the side across from it? Half. And since we know AE is 17, BD is going to be how much? 8.5. Half of 17, which is just 8.5. Do not put a line segment above BD. Easy? Okay. Go to the next one. This one's probably the harder of the two. but still not hard. So it says find the measure of angle CBD. So now we're looking for CBD, this angle right here. So again, I'm telling you, it's not going to be hard each day right here in class, but when we put all of this together, notice it didn't say anything about mid-segment, anything about the theorem. You're looking at the picture on the test and you're going, oh my goodness, what do I have here? Okay? So the first thing you need to ask yourself, and I'm going to try to keep saying this over and over again, is what do I know about B? B is a midpoint because of these markings. What do I know about D? D is a midpoint because of those markings, which makes BD a mid-segment. Okay, so you've got to look at the markings to decide what do I have in my picture. All right, so that means that this line BD is parallel to what line? AE. So then we go back to two parallel lines cut by a transversal. Okay, quickly, back up here. So first of all, the purple lines, do you guys see that these would be corresponding angles and congruent? Okay, but that may not help us answer the question since I don't know either one of those angles. So go back and find some more. Miranda? Okay, it's not because of those two lines being parallel, but it's because of AC and FD. So now look at those two. Would we agree that those are parallel since this is also a mid-segment? Okay, and if that's the case, then this becomes a transversal. And now we can use this angle here and this angle here are alternate interior. And if they're alternate interior, then that means they should be the same or congruent. So since this angle was 26, what is CBD? 26. Don't forget also about two lines that are a linear pair, or two angles that are a linear pair. Those are going to be supplementary. So you may have to use some of those things going around your picture. Don't forget that a triangle has to be 180. So maybe you figure out two and you have to find the third one. But the big idea will be looking at those parallel lines and transversals.
So are we going to have proofs in this?
Not yet. Okay, not yet. Let's go back to the one we skipped, the last example for today, and we will be caught up and it will make this week so much easier. So this last problem here, you will have questions like this on your homework, and they are the longest of the questions. It is not a proof in two-column form, but it is showing, so I am looking for all your work to be nice and neat and perfect to get credit, okay? So it's giving you the vertices of the triangle, it tells you some information about M and N, and then it asks you to show two things. One, show that the two lines are parallel, and two, show that one is half the length of the other. So the first thing you're going to have to do is what? Graph it. Draw the triangle. So make sure you graph this. I'm going to go ahead and graph mine up here pretty quickly. Again, yours will be better on your graph because it'll be more precise than mine. Make sure you have it graphed. And then what does it tell us about points M and N once you get that graphed? Okay, and they should have said respectively so you would know, but that just means in that order. So M is the midpoint of XZ. So look at XZ and let's find the midpoint. We're using the coordinates for X and Z, and I'm going to do this pretty quickly. So I'm going to have to find the midpoint of XZ so that I can graph that on my picture. So adding my x's, what is 3 plus negative 1? 2, and 2 divided by 2 is 1. Okay, so I'm not going to show my work here. I'm just going to do it mentally. What is negative 4 plus 8? 4, and divided by 2? 2. Okay, you can show your work on your homework, but just quickly trying to get that done here. So we have a point at 1, 2. Graph that and make sure it looks like it is at the midpoint. Does it look like it is splitting that line into 2 congruent parts? Okay, and that is the letter M. Okay, then they tell us N's the midpoint of YZ. So let's find the midpoint of YZ. Oops. And again, I'm just going to do that mentally up here, now using the coordinates for Y and Z. So we've got 3 plus 9 is, divided by 2, 6. And then negative 4 plus 2, negative 2 divided by 2, negative 1. Okay, so we have a point at 6, negative 1. And again, that should be in, and make sure that that does look like it's splitting your line into 2 congruent parts. And then they want us to prove some things about line segment MN. So I'm going to go ahead and draw that line segment in. And what do we know about MN according to today? What's it called? Mid-segment. Okay? It's connecting a midpoint to a midpoint. We call it the mid-segment. And so what they want us to do is basically prove the theorem. 1, that it is parallel to XY, and 2, that it is half the length of XY. So we're just going to show that. Okay, to show that, number 1, how do we prove lines parallel? Okay, possibly, but since we're on graph paper, what would be something we might use to prove that lines are parallel? Okay, the slope. What do we know about their slopes on graph paper? They're the same slope. So I would say the easier way to do that would be just simply to prove that they are parallel by showing they have the same slope. So let's find the slope of, and this is where you have to label and show your work. Don't just put a bunch of numbers down on your paper. What are you finding? And then what is it? So I'm going to find the slope of, we'll start with MN. So go ahead and count that on your graph since it's already graphed. And tell me what you get for the slope of MN. What did you get, Miranda? Okay, so you went up 3, left negative 5, or down 3, right 5? Is everybody getting the same thing? Down 3, right 5? Okay, and again, a fraction can be negative by either making the first top number negative or the bottom number negative, because the whole number then itself is just negative. All right, so we have a negative 3/5. Let's find the slope of the other line, xy. Label what you're finding. What's the slope of x to y? Okay, is that what you got when you counted it first? Okay, so what would it be if I count all the way from x to y? Negative 6/10. And that reduces to negative 3/5. And so then you can say, because they have the same slope, so little arrow means implies, that MN is now parallel to XY. So show your work, as far as at least label what you're finding, tell me what you get, and then tell me what that means. They have the same slope, therefore they are parallel. Does that make sense? Say it again. No, because that's distance, and distance is numerical values of how far it is from one place to the next. So to do number 2, what are we going to have to find? The distance from m to n and the distance from x to y. Okay, I'm going to run out of room up here on the board. It's going to get kind of messy probably, but I'll do my best. So m to n distance, remember distance is the square root of, and it's all about your work here showing. So if you skip steps or miss the little square root, you'll miss points. Show your work correctly all the way down. We're using our coordinates from m to n, which are these two in blue right here. So we're going to do x minus x, 6 minus 1 squared, plus y minus y, negative 1 minus 2 squared. Simplify. I'm going to go pretty quickly here because of time. This gives me 5 squared plus negative 3 squared, which is the square root of 25 plus 9, which is the square root of 34. That does factor into 2 and 17, but there are no pairs, and so that is in simplest form. So now let's do x to y. We're using the coordinates up here for x and y. So we have the square root of 9 minus a negative 1 becomes 9 plus 1 squared plus 2 minus 8 squared. That's going to give us the square root of 10 squared plus negative 6 squared, which gives us the square root of 100 plus 36, which is the square root of 136. And we need to simplify that. So what does that factor into? 2 and 68. Okay. 2 and 68. What's 68 factor into? 2 and 34. And 34 we just said factors into 2 and 17. So we have one pair of 2's and then a 2 and 17. So this square root of 136 is the same as 2 square roots of 34. The last thing I expect to see on your paper is where you show that that is half the length. So you're going to write mn is equal to half of xy, and then plug it in. What did we get for mn? The square root of 34, and that's supposed to equal half of, what did we get for xy? 2 square roots of 34, and what's half of 2? 1, so we get the square root of 34 equals the square root of 34. Hold on one second. Does that make sense? All right. Let me get you your